page 309. We're starting on 4-6 today, and I will say this is my least favorite section in the whole book, just so you know. And there's not much on the test over this. We're going to have a test Monday over 4-1 to, wait a second, is that right? 4-1 to 4-5, I should put. I put 4-4. It should be 4-5. Let me stop this. I'm just okay. All right. So we're graphing things that are not sine and cosine. Sine and cosine have enough going on with them, and then you start throwing in these inverse functions and tangent. Tangent is considered a major function, but it is sine over cosine, right? Now, y'all might have noticed that when we've done our tangent values, sometimes we get undefined, right? That means we have asymptotes. So here's what your tangent graph tends to look like. You have, I'm going to draw asymptotes in here like in these dotted lines here that are brown. This is pi halves. You have asymptotes at pi halves and negative pi halves on just the tangent. Oh, I wish, let me see if I can undo that. Come on, undo, undo, undo. There we go. So you have asymptotes that run pi halves and negative pi halves. So I'm going to put those here. And here's what the tangent function does. It comes, you start at 0, let's say you're at 0, 0, and it climbs kind of does something like this. It has asymptotes on both sides. If you had a reflection, the asymptotes just would kind of flip, okay? And like for instance, if it were a negative tangent x, they would be the orange graph. So, and it repeats, it's periodic, just like sine and cosine are. So every pi halves, not every pi halves, the period here is pi. It has asymptotes at pi halves. The period is pi. So if I have pi halves here, the next asymptote is, oops, I meant to do that in brown. Oh, I hit the wrong thing. Over here at 3 halves pi. And how did I get that? Added pi to pi halves, right? Pi and pi plus pi halves would be 3 pi halves. There's the next asymptote. So every pi, you have an asymptote. And I'll just do the regular tangent. Here at pi itself, we're going to have a 0, or an x-intercept. And it looks something like that. It almost looks like a cubic graph. But anyway, probably should put these little arrows on the end of it. The range, the y values, is from negative infinity to infinity, so we could write that this way. Probably want to start using these set notations. You remember, if you use a rounded bracket, that means that you don't include that in value, and the only reason we would put it on negative infinity to infinity is that we never can quite get there, right? You always get bigger or smaller. If you want an equation for your vertical asymptotes, all this is on page 309. It's x equal pi halves plus n pi. So just any multiple of pi from pi halves, you get another asymptote. Now your domain is all real numbers except multiples of pi halves. So you could write that x not equal to pi halves plus pi n. It should be pi times n, not pi over n. Okay, so it still has the same basic equation as what we see up here for sine and cosine. You can have all the same shifts and all that sort of thing. It's just that it looks very different. It's because of these undefined areas that we get. We have these asymptotes there. Cotangent, on the other hand, let's see, where do they get into it? Well, before we go to cotangent, so what if we have y equal tangent x over 2? What have I just changed in that graph? What if I write it this way? What does that affect? Isn't that the b, the number in front of the x? Isn't that like the b if we write the full equation down? A tangent bx minus c plus d. I changed the b here. Okay. If you were to go and you were to like do a table of values, as a matter of fact, if you have your graphing calculator, get it out, or Desmos if you've got your computer open. Go in and graph tangent of x. Make sure your mode is in, I'm sorry, graph tangent of x divided by 2. So 10, and then x divided by 2, which is the same thing as 0.5x if you want to enter it in that way. Make sure my mode is in the right thing. Okay. One thing you can do is, if you want to see a difference, like for instance, I've got, I graph tangent x on one line and tangent of x divided by 2 on another line. And tangent of x minus 2, do you notice? Try that. Put tangent x on your another line, like on your calculator, and look and see how they compare. Instead of having, if you look, instead of having asymptotes, the original had asymptotes at multiples of pi halves, right? So
Which one? Do tangent x over 2
and then tangent x on another line so that you can see them side by side and kind of notice when you put your tangent x on there, like how does it compare to what you put in there, what your first graph. So this was tangent, and then tangent x over 2, if you look, now your asymptotes are at pi n. I'm just going to put pi n. Your asymptotes have moved over to pi, so can we still use 2 pi over b to describe our period? Our period before was pi. What's our period now? If you think about it, every pi I'm going to have an asymptote. Every multiple of pi. Our new period here on this one is 2 pi. So let's see, does it still work? 2 pi over b. 2 pi over 1/2 would be 2 pi times 2 over 1 would be 4 pi. That's not right anymore, is it? So what is our b equation here? I wonder if it's pi divided by b. Let's see if that works. Pi divided by 1/2 would be 2 pi. Okay, so what did we just see here? We have the period equation 2 pi over b for sine and cosine. That doesn't work for tangent, does it? So our period equation for tangent is actually pi over b. So you might want to make note of that somewhere. It's pi over b for tangent. And I don't think the book points that out anywhere. You can figure it out by just doing what I did, though. And that's what sometimes, you got to do if you kind of notice a pattern's not working for something that you thought it would work for, is just, play around with it a little bit. How could I get a period of 2 pi when I notice that's what it is? Well, it would be pi over b, so that's what we have to do. The book doesn't, unless it summarizes it somewhere, it doesn't do a good job of telling you that. Let me see. Okay, so let's go on. Cotangent is on page 311, if you want to flip over there. And cotangent, if you remember, is the reciprocal of tangent. So that means instead of being sine over cosine, it's cosine over sine. So if you know some good sine and cosine values, you could just plug them in without a calculator and just simplify the fractions and get your cotangent values. Cotangent also has a period of pi, just the regular cotangent. So it's also, if we're trying to figure it out, if there's like a period change in it, if we see a b put into the equation other than 1, it would be pi divided by b also, not 2 pi over b. So 2 pi over b so far has only been true for sine and cosine. For most of the other ones, I think it is pi over b, but we'll wait till we get there just to make sure that I haven't forgotten that. Vertical asymptotes are at multiples of pi. So this one is like tangent. It's just multiples of pi. And the thing about cotangent, it looks just like tangent flipped, really. If you look in the book, it looks like tangent flipped, except that it's got a little bit, your asymptotes are coming at pi instead of pi halves. So let's see, where before I had my asymptotes at pi halves, here I'm going to have it at pi. There's one at 0, and there's one at negative pi. And then halfway in between the asymptotes, you can always tell where the zeros are because they're just right on tangent and cotangent, they're right halfway in between your asymptotes. So let me do those in blue. So here, I know I would have a 0 here, but it looks like almost a reflection of tangent, okay, except that it's slid over a little bit. Your range is all y values. Every y value's got an x value that goes with it, but you notice our domain is restricted. We don't have, your domain, you would say, is all real numbers, just not multiples of pi. So we could just say I'll say except pi times n. That would be one way to describe multiples of pi, would be pi times n. Okay, so that's cotangent. Let's look at some of the reciprocal ones. Cotangent is the first reciprocal function we've looked at. Drop this